All right, in this video we look at just more practice with a variety of definite integral problems. Okay, so what we're seeing below are, at least 6 definite integrals, and any of these integrals you should be able to compute. Okay, so what we're seeing here is a first type of definite integral problem. It is just a definite integral is given to you, for example, this one here, and they would ask you to just evaluate. All right, so there's nothing really to do here. The function that you're integrating, f of y, is given to you, and we need to evaluate this with a pretty straightforward application of the fundamental theorem of calculus part 2. So you need to find the antiderivative of this function, little f of y, and then evaluate that antiderivative at 2, the antiderivative at 1, the upper limit and the bottom limit, and then subtract those two numbers. Okay, so this is a pretty straightforward application. We're seeing f of y is 1 plus y squared over y, and you can do a little bit of algebra to split this problem up into two pieces. So we have 1 over y plus y. And so we can see here that the antiderivative is what can we take the derivative of to get 1 plus y over y. 1 over y plus y. Okay, and so we can see here that 1 over y's antiderivative is logarithm of y. Because if you took the derivative of logarithm of y with respect to y, you would get 1 over y. And then the antiderivative of y is y squared over 2. Okay, so here is your antiderivative function. You would plug in 2, plug in 1 to that function, subtract those two numbers, and then you would get the answer. Okay, so just so you can see what the answer is going to be, what you can work towards, the antiderivative from 1 to 2 of 1 plus y squared divided by y. Okay, so make sure you do 1 plus y squared quantity divided by y, integrate with respect to y, those letters matter. You get 3 halves. The answer is 3 halves plus the natural logarithm of 2. So that's what you're shooting for. Okay, any of these other problems, you should be able to try these other problems here. So just a simple, straightforward application of the fundamental theorem of calculus part 2. Okay, then there are a variety of other problems that I'd like to look at. Here is one example, just a straightforward application. And then there is another application where we still have to remember what we have done in the past. So if we were asked to find the definite integral from 0 to 12 of f of x dx, right, we don't know the answer to that because we don't know what this function is. All we know about the function are these 1, 2, 3, 4, 5 function values. Okay, we just know 5 function values. And we're asked to find the definite integral, which would be impossible, okay, to find the exact answer, which is why they asked us to estimate it. To find the exact answer, right, we would need to know more about the function. We would need to know an infinite number of values of the function. So we could do, or the formula for the function itself. So all we can do is estimate this problem, which is to approximate. Okay, now you can either choose left endpoints or right endpoints. So what we're seeing here is that delta x is equal to 3. Okay, and if you choose left endpoints, right, we can see that the interval is 0 to 12. We've chosen n is equal to 4 rectangles to get delta x is equal to 12 over 4, which is 3. So for example, you choose left endpoints, you would evaluate the function at 0 to 3, 3 to 6, 6 to 9, 9 to 12, right? And then you would evaluate at all of the left endpoints. So you'd have the function at 0, the function at 3, the function at 6, and then the function at 9. And then all of that will be multiplied by 3 to get, so we're basically doing a Riemann sum problem here. Okay, to do the approximation. The function at 0 is 32, function at 3 is 22, 15, and 11, and multiply that by 3, and you would get an approximate answer equal to whatever that number comes out to be right here. Okay, so there would be your approximation. So that is another kind of problem when it comes to definite integrals. They could give you a definite integral, say, please find it, but you don't have enough information to find it exactly, but you can approximate the answer. So we can see here that in general, this function is going from at 0 and 3 and 6 and 9 and 12. We had 32 for the function, 22 at 3. We can see that 15, so we can see that our function value is getting smaller and smaller, 11 and then 9. So if we did a left endpoint, we are getting an over approximation, right? That might be what our function could look like, connecting the dots. Now technically we can't because all we know are these function values, but we can kind of see the function decreasing over time. So the left endpoints seem to lead to an overestimate of the answer. If you did a right endpoint problem, you would get an underestimate. Okay, so that is another kind of question, okay, given a table of values. Now here is another problem, two different definite integrals, okay, and they say evaluate. Okay, and evaluate. Now the question is can we find the exact value, or do we need to find an approximation? So the question here is, when they say evaluate, do they want you to find approximately or exactly? Exact or approximate? Okay. Can we find an approximate to this definite integral or an exact? Those are the questions. Okay, so let's take a look at the information we have. It's very important to look at the question we've been asked and the data that we have. Okay, so here we're being asked to find the definite integral from 0 to 0.5 of the function f of t. So I'm looking at the values of time here, 0 to 0.5, and we have some function values. Okay, now we don't know what this function f of t is. Okay, so if we were to do this problem exactly, we would need an antiderivative of that function at 0.5 minus an antiderivative at 0. But I'm not given information about an antiderivative. Okay, an antiderivative of f of t. We don't know it. So we can't actually use the fundamental theorem of calculus to find an exact answer. But we do have the function value. We have the values of this function at a variety of points. So we can always go down the approximation route, right? We can see here that our interval is 0 to 0.5. And we could choose, say, 5 rectangles here. So delta t would be 0.1. And then perhaps we could choose the right endpoints. So we would choose the function at 0.1, 0.2, 0.3, 4, and 5. There would be your 5 function evaluations. So we can approximate this answer by the function at 0.1, which is 0.2, 0.2, the function here, plus 0.3, plus 0.4, plus 0.5, all that multiplied by 0.1. So that is the approximate answer to that integral, because we don't have the antiderivative information given to us. This problem is a little bit different. We've been asked to compute a definite integral from 0.2 to 0.5. So here's 0.2 up to 0.5. And we're being asked to find the antiderivative of g prime. Now we have the antiderivative of g prime. We would need to find the antiderivative of g prime is just g, and then we would need to evaluate from 0.2 to 0.5. But we actually have that information on the table to find this integral exactly. G of 0.5 is the antiderivative at the two end points of the interval. G of 0.5 is 0.8. G of 0.2 is 5.1. So we can see that we get 4.3 with a negative sign. Okay, so it is possible to find this answer exactly, and we're reminded of the fact that definite integrals don't have to come out to be positive numbers. They can be negative numbers. Okay, so there is another kind of problem, but notice that you've been given data and you're asked to either approximate or find the exact value of two definite integrals from some given data, and we had the information necessary to do that kind of problem. Okay. So here's another kind of problem that could be asked, right? You're given data but in a different format. Here you're given a graph of a velocity function. Okay? And the key word here is for you to estimate the total distance the object has traveled in the time interval 0 to t equals 6. So what we're being asked to do is to, in this problem, compute the definite integral from 0 to 6 of this given velocity function, and we're being asked to approximate that. We have to approximate it because we don't actually have a formula. Okay? So there are an infinite number of answers here to estimate or approximate this definite integral, and it just depends on the work that you show. So notice that we've got a time interval from 0 to 6. If, for example, you wanted to split that into 3 rectangles, right, you would then have a delta x of equal to 2. So we would have our time intervals being split up into 0 to 2, 2 to 4, 4 to 6. And then you would have to choose perhaps left endpoints or right endpoints. Okay, it just depends on the work that you show. So the function evaluated at 0 is here. The function evaluated at 2 is here. And then the function evaluated at 4 is here. And we did left endpoint problems, so we have this looking graph here. Okay, so one of our rectangles is not very tall. Okay, it has 0 height. So the area here is 20 times 2, which is 40 for the area. And then we have a function value of 30, 30 times 2, which is equal to 60. So our approximate answer from 0 to 6 of the velocity v of t dt, it's approximately 0 plus 40 plus 60, which is equal to 100. And the units there, we can see that our velocity is in meter per second. So this 20 right here is 20 meter per second. And the 2 here is the width of this rectangle, which is measured in seconds. So we're getting 40 meters, 60 meters, 0 meters. So the answer here is 100 meters distance that we have traveled. Estimate. Okay. There are other answers that you could have put here. If you had chosen to do the right endpoint problem, 2, 4, and 6, we would have had the function evaluated at 2, the function evaluated at 4, and then the function evaluated at 6. Right? And so we would have had another estimate of about 40 for the first blue rectangle, 60 for the next rectangle, and then this other rectangle, its height is somewhere around, let's say, 38. 38 times 2, which is about 64. So we would have had 100 plus 64, or 164 meters if you had done the right endpoint problem with 3 rectangles. Okay, so those are just 2 estimates that could have been obtained. Okay, and that is the end of this video, just looking at a variety of different problems that could be done with definite integrals.